We're getting ready to start discussing our first panel here, which is going to be an exciting panel discussing the gateway. If you can please join me in welcoming our moderator up. That is Mike Barrett. Mike is director of our space flight systems at NASA Glenn. Welcome, Mike. And I'll say welcome again, because I know we've had you before here at the Glens, and it's been great. So, thanks. Glasses off. Thank you very much. Thanks.
All right, I think we can go ahead and have the panel members come on up. Let me also welcome you to our fourth John Glenn Symposium. I am Mike Barrett. I'm Director of Space Flight Systems at NASA Glenn. So at least on behalf of the space side of the house, welcome. And I think Tim couldn't attend today on the aero side of the house, but I'm sure he would also express his welcome as well. So we are going to start off with a panel that is on a status on the NASA's Gateway lunar station to give you an update. But first, we're actually going to start with a short video that I think will give some context and hopefully set the stage. And if we can go ahead and run that, and then I'll introduce the panel as soon as the video is done.
Home. For me, home is where my family is. But there have been times in my life where I was called away from my family for extended periods of time. While I was serving in the Marine Corps, it was hard to be away from my loved ones. But thankfully, I had my squadron family, but other places where we were stationed around the globe became a temporary home. Then, in 2009, I launched the International Space Station, traveling even farther away from my family, conducting science 250 miles above the Earth. The space station was an orbiting home for my crewmates and myself. Talk about a room with a breathtaking view. With Artemis, NASA will send the first woman and the first person of color to the moon. We are going there for the benefit of all here. We'll need a place to orbit around the moon, where we can live and work, a place to get ready for our lunar surface expeditions, and a place to return to when our work on the lunar surface is complete. We need a lunar home away from home. This will be the Gateway. Starting with the power and habitation modules, the Gateway will be the first long-term outpost in lunar orbit humans have ever had. Primed for new discoveries, this orbiting laboratory will provide us with a unique view of our solar system. And it's already becoming a beacon for the future of international and commercial cooperation in space. With increasing capability and longer missions over time, the Gateway will be a powerhouse of technology and science, paving the way for future human missions to Mars. Design and fabrication of Gateway elements by NASA and our international partners is well underway around the world right now. Wherever you are on planet Earth, today you are part of the Artemis generation. I'm NASA astronaut Randy Bresnick. I invite you to join us by following NASA Gateway on social media and telling us where you call home.
All right, terrific. And just if you ever get a chance to talk to Randy face to face, the passion, it comes through in the video, but he's incredibly passionate about Gateway and about Artemis in general. And I think you're going to find that all of the folks on our panel today share that passion immensely. And these are the folks that are making it happen and making the work progress day to day, here to give us a status and answer questions at the end. So let me just go ahead and introduce the panel, if you could just acknowledge when I mention your name. So Mr. Sean Fuller. Sean's the Gateway Program's International Partner Manager. He's responsible for the programmatic and technical integration of the international partners in the program. Sean has over 20 years of experience in ISS, ranging from early mission operations as a flight controller through programmatic management and mission integration and operations, and also most recently the NASA Director of Human Spaceflight in Russia before he joined the early formation phase of Gateway. Thanks, Sean. Mr. Jarrett Quasny. Jarrett's a deputy manager of the Gateway Program Planning and Control Office. Prior to coming to Gateway, he worked in the ISS Program Office, JSC Mission Evaluation Room, and JSC Mission Operations Directorate, supporting training and real-time operations for ISS. Mr. Ron Mueller. Ron's the Associate Project Manager for Gateway Deep Space Logistics Element. Ron has 31 years at NASA, previously served as a Space Shuttle System Engineer, a Launch Services Program Mission Manager, and as a KSC Engineering Propulsion Branch Manager. Ms. Yasmin Ali. Yasmin's a Deputy Manager for the Habitation and Logistics Outpost, or HALO. She supported NASA human spaceflight at the Johnson Space Center for 22 years. Yasmin oversees the design and development of the HALO element, along with the integration of PPE to support a co-manifested launch. Before the Gateway program, Yasmin supported various roles in Orion and ISS programs. And Mr. Dave Irimies. Dave's the Chief of the Exploration Systems Project Office here at NASA Glenn. Dave most recently served as both the Acting Project Manager and Deputy Project Manager of the Gateway Power and Propulsion Element. Dave's from Northeast Ohio and started at NASA Glenn in 2001. So excited to hear from all of the panelists, and they'll each have a brief intro with some charts. We'll go through those and then open it up for questions at the end. Thanks. So I believe we're starting with Sean.
Well, good afternoon, everybody. Can you hear me? Is this on? All right, great. It's great to be with you and great to see folks in person this year as opposed to the online last year. Welcome to everybody online as well, but it's great to have folks here in the room as well. Let's see, Mike, if you got the clicker, can we go back one slide perhaps? On behalf of all of us from the Gateway program, it's really great to be here today and give you an update of where we are with Gateway. It really is a cornerstone for Artemis and our sustained exploration. You see here the various elements of Gateway, both from NASA, our commercial and our international partners, will be that linchpin, if you will, that allows the sustainable exploration both for the lunar surface, but then also as we get ready to take that and develop the technologies and go forward to Mars. And Gateway will be that stepping off point for us to first develop those technologies and then to send a Mars transit out for crews to go beyond that. And so very exciting to talk about that. Updates on it, certainly electrifying as we talk about our propulsion system. It's going to help us get out there and sustain Gateway and then move forward for that. The other thing I would tell you too is this is also opening up a whole new realm for scientific exploration. We're 250 miles above Earth on ISS, go about 200,000 miles out on Gateway, in a completely different realm, particularly for heliophysics and radiation exploration and science activities. And so we'll see that in some of the early flights on Gateway, starting right out of the box with our first element and opening up new science opportunities for us. Let's see, I mentioned NASA's really leading this with our international partners around the world. We have agreements with our partners taking that next step beyond the ISS, building on that history of ISS and expanding us to the future. We have commitments from the U.S. government with these other governments to develop and build Gateway, and that activity is happening. We have teams around the world that are building hardware in Italy, hardware throughout Europe, starting some early development in Japan, in addition to the activities that are happening here in the United States. So it's certainly a very exciting time to do that and to build upon those pieces and to really make this a reality. I look forward to the day that our astronauts are calling us down from Gateway and talk about that as their temporary home as they spend some time there. Some of them get ready and go to the lunar surface, and others in their activities on Gateway. So again, just real happy to be here with you today and give you an overall update and status, and we'll kind of go through some more detail now. And so let me hand it over to Jarrett.
Can everybody hear me okay? All right. So as Sean mentioned, the Gateway is Gateway is kind of born out of the collaboration with our International Space Station partners, but although it is similar in that regard, there are quite a few differences. And so what is the difference between Gateway, which is our lunar outpost, and the International Space Station, which is orbiting the Earth? So the first thing that comes to mind here is the size. ISS currently is about the size of a 6-bedroom house, so it's pretty large, and it can hold 6-7 crew members at a time, no problem. Gateway is quite a bit smaller. It's about the size of a studio apartment, although probably bigger than a New York City studio apartment, but still smaller than ISS nonetheless. So each of these different space stations are designed to last 15 years. And with the International Space Station, as you know, we've been up on orbit for 21 plus years. So we're beyond that initial 15 years. So we're hoping that Gateway is going to be able to perform similarly. But all of our systems are designed to meet a 15-year life. Another big difference is the way that we operate Gateway with crew. So ISS is continuously crewed. We've had crew up there for 21 years straight. So, in the last 21 years, there has not been a time where all humans have been on this planet at the same time. So that's pretty cool. Gateway, we're looking at about 30-day missions, and a lot of that has to do with the amount of cargo and things that we can get up there, the amount of time that is being spent in deep space, different radiation environment, and things like that. And so it's a little bit different than a continuous operation. We call Gateway human tended instead of human occupied, like we do ISS. And then obviously that means a lot of uncrewed time for Gateway. It looks like, without crew there, it's just kind of going around the moon, but that's not true. We're still doing a lot of science. There's a lot of autonomous science that's being performed. We're in constant communication with the Gateway, so we'll be able to fulfill all kinds of different science requirements and science missions, even though there's not any crew there. And then, again, logistics. Right now on ISS, we have, cargo vehicles going up to ISS all the time, delivering supplies, and the ISS is fairly large, so we're able to, store and stow a lot of that stuff on board. Gateway is a little bit different, so we're going to have to rely quite a bit on our logistics support from our deep space logistics team to provide those supplies for not only on Gateway, but for going down and exploring the surface of the moon. And then EVA, so all the spacewalks. Right now on ISS, we're able to do those quite regularly. On the Gateway is designed to not require a spacewalk to perform maintenance on the outside, so everything is going to be done robotically. We will have the ability to go and do a spacewalk once the airlock gets there, but it's not required for any maintenance. So it's being designed so that we don't have to rely on an EVA capability. So, speaking of logistics, I'll turn it over to Ron.
Thank you, Jarrett. Can everybody hear me? Okay. So, yeah, I'm Ron Mueller from KSC, and we have the Gateway Deep Space Logistics Project. Happy to be part of the Gateway program, and our role is to provide that logistics and cargo transportation capability from here on Earth up to Gateway. Our mission is to establish that foundation for deep space logistics for Gateway and also work to establish a foundation we can build on for future extension of that for lunar surface and beyond to Mars. Let me see. Down at KSC, we set up a small project, again, under Gateway. Mark Weiss is our project manager. We have a small team built on the experience of other NASA commercial programs. As mentioned, ISS commercial resupply, also the commercial crew program, and the launch services program. We have matrix subject matter experts from each of those teams that support us to help us build this capability. And this is a depiction that we're going to get into. We have a Gateway Logistics Services contract. We've awarded one provider, SpaceX, for a Dragon XL logistics vehicle. When we get into the design and development of that vehicle to provide a flexible capability to be able to launch robotic arms, external unpressurized cargo, as well as the pressurized supplies that are needed at Gateway. As you go through this step, we'll have an ascent vehicle that deploys the logistics vehicle that will then transit to Gateway, and then enter that commercial visiting vehicle realm. We'll dock to Gateway prior to crew arriving, so all that will happen autonomously, and then crew will arrive, utilize all the supplies that are necessary, put trash and things that need to be discarded from Gateway into the logistics module. Then we'll go into our departure phase and disposal. And in between there, again, we want to be flexible and help develop capability for future exploration. We keep our mind on science and utilization. We also have capability for secondary missions. So we can transport secondary missions to the Gateway, or possibly deploy those prior to or after departing from Gateway. We're also looking forward to the sample and cargo return capability. Not yet requested and needed, but those are things that we envision to necessary to extend human presence beyond. And with that, I'll hand it over to Yasmin to talk about the core of Gateway.
All right, afternoon. All right, so the PPE and Halo form the foundational element. It's really the cornerstone of the Gateway, and it's the initial capability. If some of you don't know, Dave will go into a little bit more about the PPE. It's the power propulsion element, and also combined with the Halo, and you see there in the picture. And I believe we already covered the 4 crew up to 30 days. Jarrett covered that. But one of the other important things that serves as the communication relay back to Earth, and it enables science. And we have a unique environment to do that within the orbit around the moon. And so early on, these two modules were separate. And so in 2020, they were combined. And NASA decided that it would be best to launch those on a single rocket, and that is getting launched on a Falcon Heavy. And there is a new fairing that's going into place to put the two modules together. It's one of the biggest fairings that's ever been built. And our destination is the NRHO. And we will travel out there with the PPE on a low thrust electric propulsion spiral. So it'll take us about a year to get out there. And we'll do a final maneuver, and we'll do the moon will actually go pretty low by the moon and transition into our orbit. And so one of the most important things is getting started with science early. And so we have 2 weather stations on board Halo. We've got one studying the radiation environment, the URSA. And we have another one, Hermes, that is really getting into more about space weather. And it's an instrument suite to look at solar particles and solar wind created by the sun. And then also we have another payload looking at internally, so then understanding what our radiation effects are on the outside externally and comparing that to what is being seen internally inside the actual Halo module itself. So that's really exciting. So a little bit more about Halo. Halo, one of the core things is the avionics and power and software. It provides the backbone of the Gateway. It is, so it's called the Vehicle Software Manager. It actually will start and monitor the entire Gateway, all the avionics suite. And so the entire avionics and power suite goes up with the first Halo and PPE. In Halo, we augment Orion, ECLS, and also IHAB, their life support systems. And then we are also hosting the LunarComm, which is provided by ESA, to enable science payloads and comm down to the lunar surface, as well as external robotics as well. We'll have 3 docking ports on Halo. And also we are the conduit really for the PPE refueling as well. So a little bit about where we are with Halo. Right now, the team has spent quite a few, the last few months in critical design reviews. We've been working on our subsystem design reviews for CDR, really the last step before we get into manufacturing, although we've already started and our manufacturing is underway. We have our system level CDR that's coming up in the beginning of August. You can see there the primary structure for Halo. We've done the main structural elements there. That is where actually the docking nodes are. And our plan is to complete the welding of the structure by this fall. Down there on the bottom, there is the Gateway System Verification Lab, or the GSVL. That lab, so far, we've completed 10 sprint cycles where we actually have the integrated avionics with PPE and Halo avionics. One of the things that was really important with this project is to get ahead of software. Many times software lags, but we've started and we've done 10 cycles. Every cycle has different objectives that need to get accomplished, but really we're bringing all the elements together early and getting our avionics and our software done early on this project as we go incrementally. On the top is the Halo mock-up itself. And so this will be used for our human-in-the-loop testing. And in the human-in-the-loop testing and also later as a crew trainer. And this mock-up is slated to be completed this fall. And then you'll be able to see it eventually in Building 9 at JSC. And then, one of the big things is development testing. Really, development testing in places where we need risk reduction. And so all of our subsystems across the vehicle have undergone quite extensive different risk reduction and development testing as we move forward. This is just an example of one where we have a new fan provider that is for our air revitalization system, and we were doing a vibe test to make sure that we can have the fans on while we're launching. And so with that, I will hand it over to talk about PPE.
Okay, thank you, Yasmin. Good day, all. And I definitely also recommend Jolly Scholar if you can make the time to go there this week. Good spot, good spot. Okay, so for the Gateway Power and Propulsion element, the second of the two modules for this core initial capability for Gateway, key characteristics and core functions. So it's based on Maxar's 1300 spacecraft bus, the GeoComSat bus there. We have, at the beginning of life, more than 60 kilowatts of power generation, with 40 kilowatts, up to 40 kilowatts of that being supplied for the electric propulsion aspect. We have a 2 metric ton class xenon capacity, and it's refuelable on our forward end for both RCS, Chemprop, and xenon as well. Jarrett already talked about 15-year life for the integrated stack, therefore likewise PPE as well. We had already talked about, Yasmin, that is, with the co-manifested launch with Halo for this first Gateway launch. For core functions with PPE, that's, again, both that power generation and power transfer capability to the stack. Both orbit control and orbit transfer for Gateway. Communication both with Earth and lunar surface systems, and accommodating the utilization payloads, which we just talked about as well. Okay, as far as NASA specific objectives, I would say really the two middle ones are really the core ones, and many of the rest of the ones flow from that, but essentially it comes down to demonstrating this large integrated solar electric propulsion spacecraft, 60 kilowatt class, again, power generation at beginning of life. Haven't done this before at this sort of scale, and to be able to get that flight data to anchor the various plasma models, thermal models, and such, to be able to get rid of that design conservatism so that we can, when you talk about long-range thoughts and plans, being able to design that sort of next extensible vehicle, if you will, whether that's a Mars cargo transport application or other various applications. And so that's some of the key objectives here with PPE specifically. And really, a lot of those other sub-objectives flow from that. And we also, as Yasmin already talked about and showed in that nifty animation, inserting that stack into the NRHO, the near-rectal linear halo orbit. You saw there's a very highly elliptical orbit there. A lot of innovations there in that mission design was done as well. So that's the specific objectives. And as far as status, I'll start here on the left side. So Maxar passed its second PDR here on PPE, and also finished a couple rounds here of risk reduction testing. So when we talk about new technologies on PPE, those are two areas largely, one being the on the solar arrays, specifically the structures, having lightweight structures yet rigid enough to take docking loads, to take launch loads, yet to be able to have them be lightweight enough to save on as much possible up mass, of course. And so on that picture there, on the upper right quadrant, you see the engineering development unit boom developed there by Deployable Space Systems there with Maxar. So we're going to be doing a series of tests on those and to see how far we can put structurally that EDU through its paces as we finalize the design for that. I'll direct you here farther upper right corner. So the other aspect being electric propulsion, of course. So within electric propulsion, we have to enable the co-manifest mission 3 12 kilowatt strings there. So that's comprised of the thrusters, which Aerojet's developing here with NASA. 12 kilowatts, that's the Advanced Electric Propulsion System. And then 6 kilowatts as well, so 4 of those. And that's being developed, Maxar in conjunction with Busick. So in the top sort of middle there, you see the 12 kilowatt thruster firing testing that was done here at Glenn. We have very capable EP test facilities for that, and that was really neat, being able to test the Aerojet thruster hardware with the Maxar power processing units. And so being able to have those two key aspects work together and ring out the interfaces and finalize and dial into that final design. Likewise, on the far right there, 6 kilowatt testing, again, Maxar PPU with that, as well as the Busick test thruster out at Busick. That was done. And so NASA Maxar is going to continue finalizing the spacecraft subsystems and spacecraft designs as we march towards a PPE CDR in the early 23 timeframe. Maxar is continuing to deliver flight hardware components, and much as Yasmin just talked about the Halo primary structure being initiated, so has Maxar. So I'll show you in the bottom right corner, 2 of the 3 segments on the core central cylinder have been built up. And you see there on the far bottom right side, the inner gateway deck on the forward end, as well as the shear web panels getting developed there and integrated. Also on the bottom sort of center, and directing now to the bottom left, other various components being delivered. Maxar has delivered, so the solar power module, to give you a sense, there's 800 of those solar power modules to generate that 60 kilowatt power level for both the power generation and transfer and for EP. And then some other examples there of various components, the biprop components, fill and drain valves, our attitude control electronics, power distribution unit, pressure transducers. The flight batteries have been delivered in cold storage, so marching along here. And let's see, I believe that is all. And so that ends the core presentation aspect, and I'll hand it back over here to Mike for starting the Q&A.
All right. Okay, thanks, everyone. We are going to start the question and answer part of the session, and so if you want to go ahead and anyone with a question, step up to one of the room mics. While you're doing that, I was scanning the room, trying to see if anyone from our mission design group was here, Melissa McGuire's group. The animation that Yasmin had reminded me, right? So if you heard anything in the news about Capstone over the past couple of weeks, right, the small satellite that was launched, we lost communication for a day or so with it and then reestablished. That mission will test the near rectilinear halo orbit that Gateway will be in. So that's a really strong tie for us. It was really good that they corrected that comm problem and recovered the spacecraft, because it will test the stability of that orbit in advance so that the folks in our mission design group and the JSC mission design group as well have actual data of a spacecraft in that orbit to confirm what they're expecting for the control and controllability for Gateway. So just a tie to some relevant information in the news. While folks are getting ready to ask questions, I'll start us off open to anyone on the panel. As folks watching, you can imagine Gateway is an incredibly difficult integration problem, right? Several large systems, small systems, multiple suppliers. If anyone would be willing to share some of the integration challenges that you're currently working through, and our previous experience from ISS and other integration activities at NASA, how that's helping you solve those problems. If anyone might want to touch that one.
Thanks, Mike. Just, if I can kind of get the ball rolling on that, you hit it right. It is a big engineering and integration challenge. Fortunately, our teams here and the teams around the world are building on some of that experiences from ISS for it. But that said, it doesn't mean that it makes it so smooth either. If we look at it, one of our biggest challenges across Gateway for the human-tended time frame and somewhat too for the time when it's not is our thermal control system. And so we have, for the internal heat rejection, we got thermal control systems in Halo, in the IHAB, but then that's also taking the heat from the other elements as well. And so as we look at that, how do we integrate that across? ISS has one integrated loop on the US segment, the USOS as we call it, that rejects heat through the radiators outside. It's a little different on Gateway. On the Halo, that team has body-mounted radiators. On IHAB, it has deployable thermal radiators. And so getting those two systems, working those together, that integration with it, you saw the animation there. It's a different thermal environment when you're closer to the moon as opposed to when you're much farther away at Apollon. And so all those different pieces, I would tell you that that's certainly a new challenge because it is separate thermal systems that we're integrating together into an overall vehicle system to work that out. And so, Mikey, you hit on it, right? We've got a lot of different systems as we take some of that from our heritage to help us in early development, the speed with it, but making those systems work together for the integrated spacecraft.
And Sean, if I can add to that a little bit, I think one of the key things that the Gateway program is doing is really looking at extensibility, looking at adding small things like a quick disconnect here and there to ensure that as things are moving forward and design maturation is occurring, we still have the capability to add on different options as well. And I think that's a big key piece. Specifically, we have several examples in our active thermal system that we're doing.
With those challenges come opportunities. So when we talk about the co-manifested configuration there with Halo, and we talked about those PPE specific demo objectives, well, now that, as opposed to when we were a standalone demo, we're dropped off at essentially half the altitude, pushing double the mass. And so that makes for a much more stringent EP demonstration, really putting the EP strings through its paces more as we're doing the Earth orbit raising functions and inserting into NRHO. So there's also opportunities that come with this too.
So back a long time ago when we were looking at ISS and doing the commercial resupply services, early planning the COTS program, we were surprised at the number of dockings that we had to do with the COTS type vehicle and the effect upon the ISS of those multiple dockings, as opposed to using shuttle. With the 30-day sortie missions, how many other missions do you have to bring to the Gateway for supply, maneuvering, fuel, those kinds of things?
So thank you. Great question. If I look at, pick your favorite mission farther on in what we call a sustainable phase. So we have landers that they come down to the lunar surface with the crew. If I kind of paint that picture out of the overall mission operation for Gateway. So before the crew arrives, we send a logistics vehicle up there that will have logistics needed for the crew both on at Gateway and then down at the lunar surface. And so that's one that arrives at Gateway before the crew does. You also have the lunar lander that'll be at Gateway before the crew gets there. Is it the one that's been reused from before? Perhaps that are refueling away from Gateway and then comes in and docks at Gateway. So we have those elements that are at Gateway. I could foresee that perhaps being a launch commit criteria. You have those elements in place. Before you launch the crew on an SLS and Orion, that complex and the SLS rocket, and they come out, and so that's an additional Orion docking. Now you've got all the aggregated pieces there for that integrated mission. You have Orion, you have a logistics vehicle, and you have the lander. Of course, the lander then departs from Gateway, goes down to the lunar surface, does the mission there while some of the crew are on Gateway, at least for the early missions. And then you come back, you have another docking of that lander back to Gateway for that. And then finally, the crew closes up their activities at Gateway, transferring samples from the lander to Orion, and then departs on Orion back to the Earth. And of course, the logistics module too, it will depart into what we call a heliocentric disposal, so not a return to Earth, but off into a disposal orbit around the Sun. And so that kind of summarizes your various events there for docking missions overall for any given yearly cadence sortie missions that happen at Gateway. Of course, we look at that. Dave went through the solar arrays and the rollout solar array that's very similar to ISS, and so we got a lot of a test bed, if you will, there in that new technology. But that's one of the areas that we focus on, that large array on the PP and the docking loads and the forces that come from that, as well as the plume loads of vehicles coming in and coming out. And so we're very attuned to that, looking at it. Like we said, it's certified for a 15-year life as we start. And as Jarrett mentioned, we're now, if I look at FGB and Node 1, we're 24 years into its 15-year life and many more to go. And so we kind of look at the same on Gateway, keeping those things in mind to enable us for future and extended durations.
Hi, question about the power system. Not familiar with that, the orbit that it's in. How challenging are the power management issues, and what sort of a illumination eclipse cycle is the vehicle experiencing in that type of orbit?
Oh, right. So for the first aspect, the power management, that's why part of why it's sized for 60 kilowatts beginning of life, to be able to supply what's needed. There are times in eclipse, batteries kick in, and so it's not so much that challenge. It's really going to put more so the EP system through, and that's really the area we're more focused on there. And I'm sorry, what was the second part of your question?
It was just what is the illumination eclipse cycle? How often is it an eclipse? The solar arrays not being illuminated by the sun.
Oh gosh, I
just wondered if the orbit was chosen.
We're not in eclipse because of the large orbit, the NRHO orbit. It is fully in sun, which is of course good and bad. Remember the thermal problems I talked about? There you come into that. There will be very limited times, just as you look at the three-body problem, that you do have very short, less than 90-minute eclipses. But we're talking, and I'd ask the flight design folks, phone a friend, but a couple times a year for very, very short periods is when you might see that.
Okay.
Yeah.
So probably less requirements for battery resupply over the 15-year mission then.
Yeah, actually,
there's no such resupply requirements for that. Yeah, and like Sean mentioned, yeah, it was on the order there, 90 minutes, handful of times a month. It's not, not a major.
Okay, thanks.
Sorry.
no, I was just going to comment that the actual trip out actually would. I was just going to say it was more difficult, but our mission designers are the trajectory magicians, but the eclipse constraints were actually more challenging, I think, on the spiral out. Before we're actually in the halo or the near rectilinear halo orbit. And so battery sizing was also looked at because it's also a function of launch dates and availability for windows. So all of that was looked at, but it turns out battery sizing and no need for the replacements because of the illumination is all not 100%, but not a driving issue for the long-term life.
And Halo does have batteries, and in fact, all the main modules do have batteries in case there is a need, especially during eclipse or something like that. So we're able, and Mike's exactly right. Primarily the challenging power time is at launch and time to power positive after we launch.
Thank you.
Hi, folks. During your workup for Gateway and your design and work so far, was there a test capability you wish you had that you didn't have and you had to work around that?
For clarification, I'm assuming you mean ground test capability?
I'll be willing to take flight tests if somebody wants to talk about that as well.
Okay. All right.
Let me talk a little bit about some of the flight tests that we are doing for that, and we talk about using the resources that we have and building upon it. We're going to do a demonstration on ISS. I mentioned the ROSA arrays, and so we got some flight tests from that, some applicability to it. We're also going to do a flight test of the carbon dioxide removal system for Gateway on ISS before that. So we look for those opportunities to dovetail on it. Of course, I think anyone would tell you, right, you love to have more test capability and time. Can't always have that, but we do look for those opportunities to dovetail on it from some of the others that we're flying, and particularly areas that we can expand flight test in ISS. Our first carbon dioxide removal system, CEDRA on ISS, we learned quite a bit. We learned a heck of a lot of lessons that we never anticipated to learn. We learned that things that we thought were easy in such system were a lot more difficult, and so that was one of the areas we honed in on very early to look for ways that we can test that on ISS, build that confidence before we need to rely on it for those longer duration missions at Gateway. I'm sure there's other areas from the team as well.
And I'll add too, and Mike, I think you were looking over too. So with electrical propulsion, standard practice usually is a test to 150% of mission life. Well, we don't have that luxury, right? So that coupled with facility effects, when you not quite a test as you fly. When you're on the ground, you have those highly energized ions, right, hitting the walls of the facility, coming back to the thrusters. So you have to account for those facility effects that you would not normally see in flight. So there's aspects there to account for when we're doing testing. So both that duration and the facility effects that we see. But I mean, that's the team's still working through that. It's fine. Plans test essentially to 100% mission life, do analysis for the remaining 50%, with an EDU. because of how the schedules pan out there with the flight deliveries of thrusters and things. And so anything you want to add to that, Mike?
Yeah, the one item that came to my mind, they actually have since resolved, but originally as proposed for power and propulsion element, there was not a full deployment of the ROSA arrays flight units for ground test. That, in my mind, was a large risk that has since been remediated in terms of now the program provided the funds and worked with Maxar and DSS to establish that as part of the test campaign, which was huge. That was the one that jumped out to me.
And I'll add, for the logistics module, we're pushing and driving to be very commercial. So we're leveraging heritage systems and trying to limit the amount of development testing that's required. That said, there are a lot of things, we'll go through full qualification tests, and there are some new requirements levied on us, like a waste management system. And we'll, again, leverage some of the development going on ISS to benefit from that and draw on the commercial capabilities that are there.
We'll add to, we have extensive ground testing from avionics to comm. We've got I mentioned the avionics lab. We have also a power lab that is going to bring in the PPE emulators and the Halo, basically EGSC for the Halo power distribution system. And then we have also the communication lab that's going to have the representation of all of the comm systems that are available to test that out extensively. And then originally we also didn't have a thermal vac testing, and then that got added in from a ground testing. But most of our systems from a Halo perspective, and I think also in PPE, they're heritage, right? So they've got quite a bit of history. The one outlier, I would say, the area from an environmental standpoint is the radiation. And so we are definitely have extensive radiation testing in place to do that.
I think we have time for one more.
Yeah, hi, folks. So originally, I believe both Halo and PPE were going to be joined by the NASA docking system. And now that they're going up together, can you talk a little bit about that integration process? And I'm guessing it's hard linked together, and now we got a little more structural dynamics that have to go on to get those things so they don't break apart when you put them out into space. So can you talk a little more about that? Thanks.
Here, Dave. So one of the first things that we did was we used the design analysis cycle process with the teams and really geared up on taking this from a feasibility study to actual requirements maturation and design maturation as well. And so we looked at all the different areas, the comm, the power, how those lines go across. So we basically kept the same infrastructure of what we were dragging across. There was some redundancy there, so we were able to, cut back in some areas and be more efficient. And as well, now we have basically a structure being built by Northrop Grumman that is going to have those two elements bring together. Let's see, what else say?
Right, yeah, you guys captured it well. And then also both modules are individually getting delivered to the Cape. They'll be integrated there. And so we'll go through our AI&T from a CMV perspective there before launch. So.
With that, then, again, I want to thank the panel members. There was some very last-minute logistics to set this up. I really appreciate the folks that flew in as a testament to the expertise. Ron's, he's the representative here from logistics. He flew in this morning on a flight with a connection and made it. So they have it set up, right? Okay. Again, thank you, everyone.
Only expected that to be discussed if I didn't make it. But thank you.
Well, excellent. Thank you very much to the panel. Thank you, everybody, wholeheartedly, especially for doing this on the last minute. Yeah, we apologize that the NASA Center Directors panel couldn't take place as planned, but NASA had some priorities for them that pulled them away, unfortunately. But with that, thanks again to this panel. Appreciate it very much.